Hello guys, I'm talk about today the infrared spectroscopy. So let's start it. As an introduction, we can talk about some information about the IR spectroscopy. So let's see the spectroscopy is a study of the interaction of the matter with the electromagnetic spectrum. Electromagnetic radiation displays the properties of both particles and waves. The particles component is called a photon, and the energy component of a photon is proportional to the frequency, where h is Planck constant and nu is the frequency in hertz. As you can see in this following equation, E equal h nu, and the term photon is implied to mean a small massless particle that contains a small wave packet of electromagnetic radiation or light, and we will use this in terminology in this course. So because the speed of the light, c, is constant and frequency nu, the number of cycles of the wave per second can complete at the same time must be inversely proportional to how long the oscillation is or wavelength. The nu equals c per lambda and E energy equal h nu equal hc per lambda, where c equal 3 and 10 of 10 centimeter by centimeter, and it describes the wave height or strength of the oscillations. Because the atomic particles in matter also exhibit wave and particle properties, so opposite in how much electromagnetic radiation can interact with matter in two ways. Collision, particle to particle, energy is lost as heat and movement, or coupling, the wave property of the radiation matches the wave property of the particle and couple to the next higher quantum mechanical energy level. So as you can see, the entire electromagnetic spectrum is used by chemists. As you can see this chart, as above frequency in nu in hertz, then wavelengths and energy, and as you can see in the right side, radio waves, then microwave and IR and UV and X-ray and gamma rays. So the visible region is a center of these energies, and we can focus on IR today for molecular vibrations. And after that, we can, in the next videos, we can discuss microwaves and radio and others. Okay, let's see. The IR spectroscopic process, the quantum mechanical energy level observed in IR spectroscopy are those of molecular vibration. Exactly, molecular vibrations. We perceive the vibration as a heat, and we say a covalent bond between two atoms is of a certain length. We are citing average because the bond behaves as if it were as a vibrating spring connecting the two atoms. For a simple diatomic molecule, this model is easy to visualize, as you can see at the bottom of this slide. So the IR spectroscopic process are two types of bond vibrations: stretching vibration or oscillation along the line of the bond, as you can see in these models, maybe stretch symmetric or asymmetric. And the second form of bond vibration is bend vibration or oscillation not along the line of the bond, maybe circular or rock, twist and wag, maybe in plan, out of plan, such as twist and wag. As you can see at the bottom of this slide, you can see these models describe the bending mood. The IR spectroscopic process as a covalent bond oscillates due to the oscillation of the dipole of the molecule, and a varying electromagnetic field is produced. So vibration of the atomic molecule approximating an oscillation spring produce a vibration. The greater the dipole moment changes through the vibrations, and the more intense the electromagnetic field that is generated. That are spectroscopic process when a wave of infrared light encounters this oscillating electromagnetic field generated by the oscillating dipole of the same frequency, the two wave couples, and the IR light is observed. The coupled wave now vibrates and twice the amplitude. Then the IR beam from spectrometer, as you can see below, then produced a coupled wave, electromagnetic field oscillating wave from bond vibrations. Each stretching and bending vibration occur when a characteristic frequency as the atom and the charges involved are different or for different. This is a produced IR chart from IR spectroscopy, and the y-axis on the IR spectrum is in unit transmittance, and the region where the electromagnetic field, as you can see in this arrow, field of an oscillating bond interact with IR light, the same, and transmitted is a low light is observed. In this region, as you can see in this arrow, in this region where no oscillating bond is interacting with the IR light, transmittance nears 100%. This is a produced IR chart, as you can see in this slide. The y-axis of the IR spectrum is the unit of wave number, nu, which is the number of waves per centimeter in unit of centimeter minus 1. Remember, energy equal h nu, or energy equal hc per lambda. This unit is used rather than wavelengths, microns, because wave number are directly proportional to the energy of transition being observed. Chemists like this, okay? High frequencies and high wave numbers equate higher energy. Is quicker to understand than short wavelengths equate higher energy. This unit is used rather than frequency, as the numbers are more real than the exponential units of frequency. The IR spectra are observed for the mid-infrared 600 to 4000 centimeter minus 1. The peaks are Gaussian distributions for the average energy of a transition. In general, light atoms will allow the oscillation to be faster, higher energy. This is especially true of bonds to hydrogen, CH, NH, and OH. Stronger bonds will have higher energy oscillations, so triple bonds more than double bonds, more than single bonds in energy. As you can see in this chart, above the chart, energy per nu of oscillations. As opposed to the chromatography or other spectroscopic method, the area of IR band or peak is not directly proportional to the concentration of the functional group producing the peak. The intensity of an IR band is affected by two primary factors. Whether the vibration is one of stretching or bending, doesn't matter. Electronegativity, difference of the atom involved in the bond. For both effects, the greater the change in dipole moment in a given vibration or bending, the larger the peak. The greater the difference in electronegativity between the atoms involved in bonding, the larger the dipole moment. Typically, stretching will change dipole moment more than bending. So you can notice stronger bonds can be stretching and weak bonds can be bending. The IR spectrum, it's important to make note of peak intensity to show the effects of these factors. Peak's intensity may be strong, medium, or weak, and broad. Strong peak is tall, transmission is low from 0 to 35%. Medium peak is mid-height, 75 to 35%, and weak is short, transmission is high, 90 to 75%. Abroad can be described as PR if the Gaussian distribution is abnormally broad. This is a more of describing a bond that spans many synergy. Exact transmittance values are rarely recorded. The primary use of the IR is to detect the function group. So we can as a chemist, we can use the IR spectroscopy. If we have a sample, we can analyze the sample to detect the function group present. Maybe many function group can be carbonyls, alkenes, alkynes. Maybe you can difference between ester carbonyl group or ketone carbonyl group, and we can detect many function groups such as CN, or different from CN and the C triple bond C. So because IR looks at the interaction of the electromagnetic spectrum with actual bonds, it provides a unique quantitative probe into the functionality of a molecule, as the function groups are merely different configuration of different types of bonds. Since most types of bonding covalent molecules have roughly the same energy, so C double bond C and C double bond bonds, CH and H bonds, they show up in similar regions of the IR spectrum. Remember, all organic function groups are made of multiple bonds and therefore show up as multiple IR bonds or peaks. To summarize our presentation today, we can analysis maybe at the sample, like maybe we can test sample organic sample actually, and we can get the final chart for IR chart, and from IR chart we can detect many function group. So if you are a young scientist and or a young chemist uh, working on unknown sample, and you want to detect many function groups present in it, you can do or analysis IR, and from an IR chart you can detect the function group present. So as you can see, the sides, blue sides, you can detect the OH and NH and CH. And the green side, you can detect C triple bond C or C triple bond N. From here, the yellow side, you can detect double bonds, C double bonds O, C double bond N, and C double bond C. From the right side, actually the red side, this is a fingerprint region. Every molecule have different fingerprint region. You can detect C double bond C, C double bond N, and C single N, C single O. So if you have a big, strong broad, you can detect the OH or NH or CH from this area from 2700 to 4000. From 2000 to 2700, you can detect C triple bond C or C triple bond N. Here, from the yellow band, you can detect from 1600 to 2000, you can detect C double bond O, C double bond N, and C double bond C. And from the right side, from 600 to 1600, you can detect the fingerprint region. You can detect many function groups such as C double C single C, C single N, and C single O. Thank you for your attention, and please subscribe the channel and like the channel, like the videos. For more videos, support us and make subscriptions. Thank you today for your attentions.